Our world, the one we see and touch, often seems predictable. A dropped apple will always fall to the ground. The sun reliably rises in the east. These are the rules of classical mechanics, the physics that governs the large-scale objects and forces we experience every day. Yet, beneath this surface lies a realm of astonishing strangeness, a world governed by entirely different principles. This is the quantum world, a place where the rules we take for granted are bent, broken, and beautifully reimagined. It is a domain of the incredibly small, the fundamental building blocks of matter and energy. Scientists are now discovering instances of macroscopic quantum behavior. This fascinating phenomenon occurs when the subtle and often bizarre effects of quantum mechanics become observable in objects large enough for us to see. Understanding this transition, from the quantum to the classical, is one of the great challenges in modern physics. It is here, at this intriguing boundary, that the potential for revolutionary technologies, such as quantum computers, begins to emerge. These are not merely faster versions of the computers we use today. Instead, they are entirely new kinds of machines designed to harness the peculiar logic of the quantum world itself. To grasp the sheer oddity of the quantum world and its implications for computing, we often turn to a famous thought experiment. It was devised by the physicist Erwin Schrödinger in 1935. Imagine a cat, he proposed, placed inside a sealed steel box. Alongside the cat is a diabolical device, a tiny amount of radioactive substance, so small that perhaps in 1 hour, just one atom decays. If it decays, it triggers a Geiger counter, which in turn releases a hammer that shatters a flask of deadly poison. If the atom does not decay, the cat remains unharmed. According to classical physics, the cat inside the box is definitively either alive or dead. However, quantum mechanics offers a profoundly different interpretation. Before we make an observation, the radioactive atom is said to exist in a superposition of states. It has both decayed and not decayed simultaneously. Consequently, the entire system, including the unfortunate cat, is also in a superposition. The cat is, in a quantum mechanical sense, both alive and dead at the same time, a blurry mixture of two mutually exclusive realities. This concept of superposition is not just a philosophical puzzle, it is a cornerstone of quantum mechanics and crucial for quantum computing. At the very heart of a quantum computer lies the qubit, its fundamental unit of information. Unlike the classical bit, which is like a simple toggle switch, a qubit is a far more complex and delicate entity. It could be an individual atom, an electron, a tiny superconducting circuit, or even a photon of light. The key is that its quantum properties, particularly superposition and entanglement, can be controlled and manipulated. These properties are what give quantum computers their extraordinary potential, allowing them to perform calculations in ways that are simply impossible for even the most powerful classical supercomputers we have today. Superposition allows a qubit to exist in multiple states at once. If you have a small number of classical bits, say 3, they can represent only one of 8 possible combinations at any given time. However, 3 qubits in superposition can represent all 8 of those combinations simultaneously. As you add more qubits, this capacity for simultaneous representation grows exponentially. The second crucial property is entanglement. When qubits become entangled, they form a single, deeply interconnected quantum system, even if physically separated. This interconnectedness allows quantum computers to perform complex calculations where the qubits work in concert, influencing each other in ways that allow for shortcuts through vast computational landscapes. The potential applications of quantum computing are truly transformative, sparking immense excitement across scientific disciplines and industries. Imagine designing new, life-saving drugs molecule by molecule, not through trial and error, but through precise quantum simulations. Consider the creation of novel materials with unprecedented properties, such as superconductors that work at room temperature, revolutionizing energy transmission and transport. Quantum computers could also optimize complex systems, from financial markets to logistical networks, finding solutions that are currently beyond our reach. Even the fundamental quest to understand the universe, from the nature of black holes to the origins of consciousness, could be advanced by these powerful new tools. This extraordinary promise has, quite naturally, generated a significant amount of hype. Headlines often proclaim the imminent arrival of quantum supremacy, where quantum computers will outperform all classical machines on meaningful tasks. Venture capital is pouring into quantum startups, and governments worldwide are investing heavily in quantum research. There is a palpable sense of a technological revolution on the horizon, one that could reshape our world in ways as profound as the advent of the classical computer or the internet. The allure of solving currently unsolvable problems drives this enthusiasm, painting a picture of a future where quantum power unlocks unprecedented progress. However, it is crucial to balance this excitement with a healthy dose of scientific skepticism and realism. While the theoretical foundations of quantum computing are sound, the practical realization of large-scale, fault-tolerant quantum computers is an immense engineering challenge. For a grounded perspective on the current state and future prospects of quantum computing, we can turn to experts like Dr. Barbara Terhal, a distinguished theoretical physicist in the field. Her work focuses on quantum error correction, a critical component for building reliable quantum computers. Dr. Terhal and her colleagues offer a sobering, yet ultimately optimistic view that emphasizes the marathon-like nature of this scientific endeavor. They caution against expecting overnight miracles, stressing that the development of practical quantum computers is a multi-decade undertaking, demanding persistent effort and intellectual rigor. Dr. Terhal's insights highlight that while the theoretical promise of quantum computation is vast, translating that promise into working hardware is fraught with difficulty. One of the primary challenges is decoherence. Quantum states, like superposition and entanglement, are incredibly fragile. Any interaction with their environment, a stray vibration, a tiny fluctuation in temperature, or an errant electromagnetic field can cause these delicate states to collapse, losing their quantum properties and corrupting the computation. Shielding qubits from this environmental noise is a monumental task, requiring extreme conditions like ultra-low temperatures, close to absolute zero, and sophisticated vacuum chambers. Furthermore, even with the best shielding, errors are inevitable in any quantum computation. Qubits are not perfect, and the operations used to manipulate them are not perfectly precise. Unlike classical computers, where bits are robust and error rates are exceedingly low, quantum errors are much more frequent and complex. Despite the formidable challenges, the field of quantum computing is witnessing remarkable progress. Scientists and engineers around the world are making steady strides in building the foundational elements of these future machines. One key metric of progress is the number of qubits that can be integrated and controlled within a quantum processor. Over the past decade, we have seen this number grow from single digits to systems incorporating dozens, and in some experimental cases, even hundreds of qubits. Each increase represents a significant step forward in complexity and potential computational power, pushing the boundaries of what can be achieved. Researchers are exploring a diverse array of physical systems to serve as qubits, each with its own set of advantages and disadvantages. Superconducting circuits, which are tiny loops of metal cooled to near absolute zero, are a leading approach pursued by companies like Google and IBM. Another promising avenue involves trapped ions, where individual atoms are held in place by electromagnetic fields and manipulated with precisely targeted lasers. Other contenders include photonic qubits, neutral atoms, quantum dots, and even imperfections in diamond crystals, known as nitrogen vacancy centers. This rich variety of approaches fosters innovation and increases the likelihood of discovering the optimal platform for quantum computation. Beyond simply increasing qubit numbers, significant effort is dedicated to improving their quality. This means extending their coherence times, the duration for which they can maintain their delicate quantum states before succumbing to decoherence. The construction of a functional quantum computer is not merely a scientific challenge, It is an engineering odyssey of epic proportions. The very properties that make qubits so powerful, their quantum nature also make them incredibly sensitive and difficult to manage. Creating an environment where these delicate states can exist, be controlled and be measured accurately requires pushing the limits of modern technology. It is a realm where physicists become extreme engineers, and engineers must grapple with the counterintuitive laws of quantum mechanics. This interplay creates a landscape of both breathtaking innovation and persistent, frustrating obstacles. One of the most immediate engineering hurdles is the requirement for extreme operating conditions. Many leading qubit technologies, such as superconducting qubits and some types of quantum dots, must be cooled to temperatures mere fractions of a degree above absolute zero, colder than deep space. This necessitates the use of complex cryogenic systems involving multiple stages of cooling and sophisticated refrigeration techniques. Maintaining these ultra-low temperatures, while also rooting in the intricate wiring needed to control and read out the qubits, is a marvel of thermal and electrical engineering. The sheer scale and complexity of the required support infrastructure can be immense. Beyond temperature, qubits demand an environment of almost perfect silence, electromagnetically speaking. Stray radio waves, magnetic fields from nearby equipment, or even cosmic rays can disrupt their fragile quantum states, leading to decoherence and computational errors. While the physical construction of quantum computers presents enormous challenges, the very concepts underpinning quantum mechanics can offer us new ways of thinking, even before these machines become widespread. The peculiar logic of the quantum world's superposition, entanglement, uncertainty can serve as powerful metaphors and conceptual tools for approaching complex problems in our everyday lives and in various fields of human endeavor. Adopting a quantum thinking mindset might allow us to see possibilities and connections that the more rigid framework of classical thought can obscure. Consider the principle of superposition, where a system can exist in multiple states simultaneously until measured. In problem solving, this could encourage us to explore a wider range of potential solutions concurrently rather than committing prematurely to a single path. Imagine a business strategist considering several market entry plans at once, or a designer iterating on multiple prototypes simultaneously. This approach embraces ambiguity and allows for greater flexibility, acknowledging that the best solution might only emerge after exploring diverse possibilities. Entanglement, the idea of interconnectedness where the state of one particle instantly influences another, regardless of distance, offers a potent analogy for understanding complex systems. In ecology, economics, or social dynamics, we often see how seemingly disparate elements are deeply linked, and how a change in one part can have far-reaching, sometimes unexpected consequences elsewhere. Quantum thinking encourages us to look for these hidden connections, to appreciate the holistic nature of systems, and to understand that problems rarely exist in isolation. The Heisenberg uncertainty principle, which states that certain pairs of properties, like a particle's position and momentum, cannot both be known with perfect accuracy simultaneously, also has metaphorical resonance. It reminds us that the act of observation can influence the system being observed, and that there are inherent limits to our knowledge. Peering into the future, say a century from this day in 2025, the landscape of quantum computing could be vastly different from its current nascent stage. If the formidable scientific and engineering challenges are overcome, quantum computers may evolve from specialized research tools into powerful engines driving innovation across countless sectors of society. It is difficult to predict the exact trajectory, as technological evolution often brings unforeseen breakthroughs and applications. However, we can speculate on some of the profound transformations that might occur, painting a picture of a world deeply influenced by the mastery of quantum mechanics. In medicine, the ability to accurately simulate complex biological molecules could lead to an era of personalized treatments and rapid drug discovery. Diseases that are currently intractable might yield to therapies designed at the quantum level, targeting specific cellular mechanisms with unprecedented precision. New diagnostic tools, perhaps leveraging quantum sensors, could detect illnesses at their earliest stages, long before symptoms manifest. The very understanding of life itself could be deepened as we unravel the quantum processes that underpin biological functions, from photosynthesis to the workings of the human brain. Materials science could be revolutionized, leading to the creation of substances with properties we can currently only dream of. Imagine ultra-efficient solar cells, catalysts that can clean our environment, or building materials that are incredibly strong yet lightweight. Quantum simulations could guide the design of these new materials from first principles, accelerating innovation and enabling sustainable technologies. The energy sector, manufacturing and transportation could all be transformed by these quantum design materials and the optimization capabilities of quantum algorithms, leading to a more efficient and environmentally conscious world.